Hi, welcome back. You might recall from calculus that we wrote the equation of a tangent line quite a bit. And when we wrote the equation of a tangent line, we basically started with a differential. dy dx would equal f prime of x. And if I were to solve this, we would get dy equals f prime of x dx. Now, last year we called this solving a differential. But many of you guys were so sharp-eyed, you realized, isn't this just a tangent line? Because this is just my change in my y values as change in y goes to 0. Yeah, that's just my change in y values. Isn't that just the slope of a function at a point? And isn't that just a change in your x values as x gets really small? Exactly. This is the equation of a tangent line as our values get really small. Now this was for single variable. In multivariable, we can do the same thing, except for in multivariable, we don't just have the slope in the change in x, we also have to deal with the slope in the change of y. And that's what we have right up here. If we have, remember, if we have a function in terms of x and y, and we're looking at how a changes by the x variable changes by h. So I can kind of look at this graphically if I want to, right here. So we're starting at x equals a. We're moving over some distance h. So that's a plus h. So my y values, I might be starting at some point b, and I'm moving up some value k. And that's going to put us at b plus k right there. So we're moving from here to up here. That's kind of where we're moving to right here. And how can I write this equation as a tangent line? Well, we can approximate the values, and we did this earlier in the test. So we can find a point, AB, plus your change in the partial with respect to x, plus the partial with respect to y in the k direction. And we can simplify that a little bit. This is just a little bit of algebra, where we can say that, well, this is really this h point right here is really just my change in x, and that k is really just my change in y. By bringing the f over here, we get to change in f. That's really all that means right there. And all we do now is we're just going to let delta x and delta y go to 0. Get them really small, and what happens is now we get that derivative. And that's what we wound up with right here. This equation right here. Delta f, or change in f, df, the change in f, is equal to my slope in the x direction with my changes in x, just like we did here. The slope is a function of x times my change in x. But now I do it with my y's, plus the change in y value with my slope in the y direction times my change in y. And we tend to write it either one of two notations. And we have a very special name for this. This is what we call the total derivative. Now we've been doing partial derivatives, but notice now we're talking about a total derivative. It's my change in my function, but now it's not just my change with respect to x, it's with my change with respect to y as well. And it's also a tangent plane. And that's going to give us the equation of our tangent plane, which we've already done before, so that's not really anything new, just a different name. So we want to write the equation of a tangent plane of this function at this point. Well, the first thing we need is a point. Now you may think like, oh look, we have 2 points, but you got to remember, we're multivariable. This is just x and y. These are both x and y here are independent. My dependent variable is z. So to get the point, I'm still going to have to plug it in. That's going to become f of 2, negative 2. And if we plug that in, that becomes 2 times negative 8 plus 4, and that becomes negative 12. So my point, 2, negative 2, negative 12. Next, now I'm going to go ahead and write my function. So in order to get this, I'm just going to use this rule. Are you ready? df, the change in my function, is just equal to my partial with respect to x, dx, plus my partial with respect to y, dy. This right here is a very important function for us. We're going to talk about that in just a few, we're going to talk a lot about this throughout the year. This is called our total derivative because it's we're combining our change in x with our change in y. And I can do most of this in my head. Change in f is equal to, well, my partial with respect to x, that's just going to become, in parentheses, y cubed plus 2x dx, plus my partial with respect to y becomes 3x y squared, that just becomes 0, dy. So all I have to do now is just plug in my point. So I'm going to plug in the point to -2. And if I plug that in, we're going to get, what's that become? 8, or -8, sorry, plus 4 dx plus, this becomes 3, my x is 2, times 4 dy. So therefore we get df is equal to -4 dx plus 24 dy. Now, I'm not done yet because I want a tangent plane, and that doesn't look like a tangent plane. But remember, df is really my change in my function's value. So this could be z minus, what's my z point? 12, so z plus 12 equals -4. dx is my change in x's, so it'll be x minus 2 plus 24. My y's is my change in my y value, so I'd write that as y plus 2. And that would be our equation of our tangent plane right there. And we could do that here too. We want to find the linear approximation for this function. We don't know what that is. So since I don't know what this is, I'm going to write an equation for this. And we saw these kind of last year in calculus when we did tangent line, where we approximate something like the square root of 26. So I have to come up with a function. So I'm going to write this as function that's, now be careful, there's 3 variables here, so x, y, z, and that's going to be x cubed, y to the 4th, z to the -1. So the first thing I'm going to need is a point. Now, I need to pick a point close to this that I know. Well, I can let x be 4, y be 1, z be 2. So I want to find the value of the function at that point. And that's going to equal, if I plug this in, oh man, 4 cubed, 64 times 1 to the 4th is 1 over 2, and I get 32. Next, I want to write my rule. Remember, this is my approximation technique right here. So the change in my function is equal to, well, gotta get my partials. So I gotta do my derivatives. I need the partial with respect to x, dx, plus the partial with respect to y, dy, plus the partial with respect to z, dz. And I can solve this. I can do this in my head. The partial with respect to x, 3x squared, y to the 4th, z to the -1, dx, plus the partial with respect to y becomes 4x cubed, y cubed, z to the -1, dy, plus the partial with respect to z, negative x cubed, y to the 4th, z to the -2. Be very careful with that. dz. Plug in the point. Plug in the point that we use, 4, 1, 2, and we will get the following. If I simplify all of this, this just becomes 24 dx. Plug it into here, we're going to get 128 dy, plus plug into here, we're going to get -16 dz. Now we're not done, because they want me to estimate the value, so I should get a number. So now is when I have to plug in my changes, my differences. So now, if I rewrite this as a function, this becomes, in terms of my tangent plane, my change in x, 24, remember we're doing x minus 4, plus 128 y minus 1 minus 16 z minus 2. And this is just going to become my far left. So now I'm, whoops, forgot this one. And that should be z minus 32 right over there. I always forget about that part. Please don't forget about that. And then we're going to plug in the point 3.99, 1.01, and then the 1.98. And so we get z minus 32 equals, and this becomes 24 times, what's that, negative 0.01, plus 128, plug in the y, we get 0.01 minus 16 times negative 0.02, and solving for z, we wind up with 33.36. Oh, that's just kind of a mess right there. Now, we can also find our percent error, find out how accurate this is. You remember, do that from last year. And our percent error, how far off we are from the actual answer, is by 0.075%. So it's actually a pretty accurate tool. And of course, we can do it for this one too, but I won't bore you with another one. You have one like this on your homework. So I hope you guys enjoyed the video. I'll see you guys later. Bye-bye.